Problem 824. Use the moment area theorems and determine the slope at C and the displacement at B. E and I is constant. We have a beam that is fixed at end A and has a distributed load from C to B with a distance A between A and C and C and B. So we have a vertical force of AY, a horizontal force of AX, and a moment at A. We sum the forces about Y, and we get AY minus WA, and that turns into AY is equal to WA. Next, we sum the forces about X, and we find out that A of X is equal to 0. Next, we take the sum of the moments about A is equal to 0, and we get MA minus WA times 3A over 2, which is A plus half of A, which gets A over 2, and we come to the conclusion that MA is equal to 3WA squared over 2. We next take section BC, and we take a moment about the side of C, have the distributed load as WA and a distance A, but X is coming from the B side. We take the M of X from here is equal to negative WX times X over 2, and taken at X equals 0, M of B, the moment about B is equal to 0. If you take at X equals A, M of C is equal to negative WA squared over 2. Next, we take section AB and have a moment about A, and with the X coming from the A side, we have M of X is equal to negative 3/2 WA squared plus WAX. At X equals 0, the moment about A is negative 3 WA squared over 2, which matches the original calculation here. It's just going the opposite way. Next, we construct the moment diagram, and for the moment at A, it's equal to negative 3 WA squared over 2EI, so you bring it down to here, and then the moment at C is WA squared over 2EI, negative, and so you bring a straight line up to here, and because it's a distributed load, you have a concave downward arc going to B from C. You then calculate the centroids of each shape, split into 3 different sections: a triangle, a square, rectangle, and a parabola thing. Next, we construct the elastic curve diagram, and it's shown to be concave downward with the tangent of C being right here, the tangent of B being right here, and theta CA being between the beam and the curve, and TB to A from B down to the bottom of the curve. To find the slope at C, we recognize that theta A is equal to theta CA, and theta C is equal to theta CA also, which is equal to the area of this, which is negative WA squared over 2EI plus negative 3 WA squared over 2EI, added together and multiplied by A over 2. We find that theta C is equal to negative WA cubed divided by EI. Next, we find the displacement at B, which is equal to TBA, which is equal to the areas multiplied by the centroid, which is shown here, and which is also shown in the moment diagram. We get it to be equal to negative WA to the 4th over 8EI minus 5 over 6 WA to the 4th EI minus WA to the 4th over 4EI. And when you add all those together, you get the displacement at B to equal negative 41 WA to the 4th over 24 EI.